Hey, uh, yeah, this is what I've been working on for the past couple weeks, please. Past week, I was trying to work on a way to visualize the SemNet results data, and this is what I kind of came up with. I've been working on this for like maybe 30 or so hours this week, and I think it's pretty cool. I guess I'll start off by describing how this kind of came together. So let's take some SemNet results, right? So each SemNet simulation, at least each of the SemNet simulations I ran, compared Alzheimer's disease and hypothyroidism. And it generated a certain number of source nodes, right? This is all stuff that you know. In this case, I compared Alzheimer's, hypothyroidism, uh, where the source node type was amino acid, peptide, or protein, right? And given that type, there are about 255 different source nodes that connect the two diseases um, with a type of amino acid, peptide, protein. And so for each one of those, I guess, questions, like how are Alzheimer's disease and hypothyroidism related via AAPP? For each question, two simulations have to be run. One simulation to essentially compare all the source nodes to hypothyroidism, and then one simulation to compare the results to Alzheimer's disease. And so that's why for each amino acid, peptide, or protein source node category type, I have two simulations, each of which have a different respective target. That's where I'm coming from. And what I did was I took that data and I cleaned it up a little bit in Python and created some CSV files from the XLSX documents that the simulation spits out. And this is actually not the simulation result. This is the CSV file itself. So I added a label for the source nodes, which were already provided, and then I added an entirely new column called node target, just to make things easier for my program. And this node target column obviously corresponds to the node target given in the document title. I created that CSV, right? And then I turned that CSV into a JSON file, given a couple, I don't know, some data cleaning, things like that. I don't know. But what I did was I reformatted everything into a JSON file. And this JSON file contains data for nodes and where is it? Links. That is. So nodes and links. Contains data for all that stuff. So I took that JSON file and I plugged it into my JavaScript script, and I used a couple really interesting packages like 3.js, some other like kind of 3D rendering, I guess, packages, as well as some inspiration and some code from this one just open source kind of like graph library, which is really cool. And all these libraries are free open source under like the MIT licensing agreement, which means that like you can just use it in basically everything. I used a couple of these libraries and like did my own tweaking with the 3D rendering stuff and like object classification, things like that, to spit out my graph, and that's what this is. And so obviously, looking at this graph, you think, okay, these must be the two source or target nodes, and that's what they are. So this is Alzheimer's, this is hypothyroidism. These are the respective CUI numbers. And you see all these different source nodes, but these source nodes are kind of differently sized, differently colored. Their connections are more or less opaque, more or less transparent, I guess. And I actually calculated that based on the Hedison score. So again, the Hedison score, as you know, is basically a way to figure out how important a source node is to the target node that's been compared to. So let's say, for a target of hypothyroidism, this hypothyroid hormones are very important to hypothyroidism. So they have the lowest Hedison score, which is the highest ranked of the Hedison scores, I guess, that SemNet spits out. So, but kind of a problem though is when you have two different simulations, the Hedison scores aren't quite scaled this in the same way, right? So we have this lowest Hedison score of 10, this lowest Hedison score of 9.5 down to 33 compared to 43. So what I did was I normalized these head-of-sum scores based on a scale of 0 to 1. So that way they can be compared to each other. So if you scale this head-of-sum score of 10 to 0, and this head-of-sum score of 43 to 1, then you can then also compare that head-of-sum score to 0 and 1. And based on what I've heard through the grapevine in the lab, like these head-of-sum scores do scale with each other. So I'm not quite sure how the head-of-sum scores, how the rankings work, but based on what I've heard, like this head-of-sum score of 10 is more or less, you know, say 3 times more impactful than it has some score of 33. Now, doing the scaling stuff, it's not going to quite align, but it's a pretty close estimation, and I'll have to like work out the mathematics to maybe see if like there's a better way to have those two head-of-sum scores talk to each other. But this is what I came up with in the meantime, right? Pretty easy, pretty straightforward. That's what a lot of the Python script was doing, actually, is just like getting its head-of-sum scores normalized so that they can then be put into the graph. So as you can probably tell, the smaller the source node, the lower the average head-of-sum score between the two, right? So say this is a beta androgenetic receptor kinase 1. So it's got a relatively pale, small source node, right? Let's see if I can get it a little bit. There you go. That's a relatively small, pale source node. And so what you might expect is the two edges to be relatively highly ranked. So again, 0 is the best, closest ranking. 1 is the worst, right? So this edge compared to Alzheimer's disease is 0.89, 0.9-ish. That's pretty badly like ranked as far as the head-of-sum score rank goes. Again, 0.9 is pretty close to 1, not that great. This one is 0.86, kind of the same like ballpark. Not a great, like, it's not, it's like the head-of-sum score isn't a great, this source node isn't super important for hypothyroidism. All right, sorry, my words kind of got jumbled. So what I did was to create the actual node opacity size, all that stuff, is I averaged the normalized head-of-sum scores for both edges. I took the average, and then the average kind of determines the size and color of the source node. So this one's a relatively small white source node because both edges are pretty low ranked, right? Now let's take something that we know is probably quite highly ranked on the head-of-sum level. Where's amyloid? That's a good one. Oh, wow, that was quick. Okay, so amyloid. Amyloid is obviously one of the most, if not most, important protein in respect to Alzheimer's disease. So let's see. This is Alzheimer's right here, C00. This is amyloid. This line is rather dark red. That indicates a strong connection. I expect a rather low normalized head-of-sum score, maybe close to 0, if not 0. Okay, so that's 0. So what that says is that amyloid is the highest ranked, I guess, amino acid peptide protein compared to Alzheimer's disease. And let's verify that in the data, because 0 would indicate that's the top. So this is the right sheet. And yeah, there it is. Okay, amyloid right there. Now, how does it relate to hypothyroidism? It is a normalized score of 0.54, 0.55-ish. Okay, so what we might expect then is, in the hypothyroidism sheet, amyloid's probably somewhere in the middle of the pack. That's what I'm predicting, right? Amyloid. What in the world? Why can't I use the search function? Okay, now it works for some reason. But yeah, so amyloid 134, that's about in the middle of the pack from 0 to 255. So that's pretty cool. Now, this node is an average of these two edge ranks. So this would be about, what's that, 0.0, 0.55, about 0.265-ish, or 0.2, I don't know. Say 0.25, right? 0.25. That's what this node is considered. So 0.25 is pretty close to 0, which is the best you can get. And so it's a relatively red relatively large node. Now let's take, say, what's this one? Insulin. Red. Also, I bet this one's bigger if we get this scaling right. I'm still trying to get this all worked out. Okay, so insulin. One edge is 0.08, close to 0. 0.08, also close to 0. The average is 0.08, which is lower than the average of 0.25 of amyloid. Therefore, the node is redder, and if you can see this, it's slightly bigger too. You can kind of see it. Like, I'm still kind of working on it, but it's slightly bigger. You see that? Slightly bigger. And that's how I guess the graph kind of visualizes everything. Now, as far as like future work, you know, like if this is something I should continue to pursue, I could maybe add different source node types. So instead of just AAPP, I could do like genome, organic chemical, all these different things. And then have them be different colored nodes, so you can kind of see just like how all these different things compare. If for some reason you want 3 target nodes, that's easily done. It's quite versatile, this tool. And again, you can like adjust the visualization quite easily. It's actually not that easy, but you can adjust it accordingly and make it look pretty for a bunch of different kinds of classifications that you want. And yeah, so I just let me know if you want me to kind of like continue looking into this, if this is a good avenue to be kind of putting my time and effort into. Because yeah, I think this is a pretty cool tool, and I mean, it could always be made better. So yeah, thanks.